Welcome. Okay, welcome to today's teletraining. This is on the Advected Layer Precipitable Water product. It's an experimental product. It's not available over the SBN, but we'll show you at the end here in terms of how to get this via the LDM. I'm Dan Bikus, Ed Zoke, Sheldon Cusselson. We're involved in this training, and the product development team consists of John Forsyth and others listed down here. So our learning objectives are to introduce how the product is made, along with strengths and weaknesses, analyze a variety of cases that highlight operational applications, and then at the end, how to receive the data in your AWIPs. First, let's discuss what PW products are available now. Well, the blended TPW product has been available via the SBN for some time now. It consists of microwave instruments on polar orbiting satellites, where PW through the total vertical column is derived. No model inputs are used to retrieve the moisture profile. It does see through clouds, but not precipitation, and it also makes use of GPS sites over the CONUS. It's at 16 kilometer resolution with temporal resolution between 1 and 3 hours. You also have infrared water vapor imagery available on GOES 16 and GOES 17. It's a relative measure of water vapor. You have different layers in the vertical depicted from the 3 water vapor channels, but most importantly, clouds are obscured, so it may obscure moisture information. So because of that, this tends to be less used compared to these more quantitative measures of moisture that we get from various microwave instruments. So another product that's available from Sims, the Mimic TPW product, looks like this, and it's similar to the blended TPW product that we looked at, except it does make use of GFS winds to advect the moisture. It's available at hourly output and at quarter-degree resolution. Another new GOES 16 baseline product is this TPW product, and it does use GFS as a first guess. Since it is a GOES product, it's not microwave, so clear sky conditions only. You'd have missing data where there are clouds. One of the nice benefits, though, it does have high temporal resolution, and it has a good horizontal resolution as well. The Alpw product is analogous to total precipitable water, but on layers. The blended layer precipitable water product is created from NOAA microwave integrated retrieval system known as MERS soundings, and 4 layers are created: surface 850, 850 to 700 millibars, 700 to 500 millibars, and 500 to 300 millibars. It's produced hourly and mapped onto a 16 kilometer resolution grid. 7 MERS sounding spacecraft are currently used, essentially these satellites that are listed. All swaths are advected to a common time and averaged. The advected product has reduced edges between the swaths. GFS model wind forecast from up to 9 hours before the target time are only used to advect the swaths to a common time so that output is available hourly. Before the spring of 2019, Alpw was produced 3 hourly. This is a non-operational product. However, various operational centers and WFOs have been receiving this product via LDM in their AWIPs. This clock diagram gives you an indication of the interval between the data when it arrives, when it's available for the algorithm to work with. So remember, there's 7 different satellites currently, and this clock diagram just indicates the periods of high sampling and no sampling, which can make animations challenging. At times you get fairly frequent pass, and then there might be some time between the next here. So it gives you an idea of the irregularity in terms of when the data is available. So strengths, easy to interpret. The animation is available at regular intervals. It does show a 4-dimensional structure of water vapor, and the water vapor values are not dependent on the model. The retrieval is done in clouds, which is an advantage compared to GOES retrievals. And there's numerous applications. We'll talk about atmospheric rivers, flood events, convective events, also synoptic analyses such as short waves, surface boundaries, frontal zones, tropical waves, winter precipitation, a lot of different applications for this. Limitations, there's a number of reasons why there may be missing data. You'll see that in the examples coming up soon. Most common one is no satellite data may be recent enough. If it's too old, it'll just show up as missing there. Precipitating regions are masked out within the algorithm. The thing you have to be careful of is make sure you don't compare an instantaneous radar image to a given time, because there are complexities in the advection scheme that don't really allow for a one-to-one comparison like that. High elevation regions, if you're in the west, the Rocky Mountain region, or the high plains, it could be a limitation when you're looking at the lower layers, either that it's below ground or you're just looking at a slice of the lower layer, so it may appear lower than what you might expect. And the ingest itself is quite complicated. A lot of things have to come into phase to make it happen, so you will notice that there's times that are missing due to this as well. Quantitative usage, it's not intended as a replacement for the blended TPW. Use this in a complementary and supplementary way with the blended TPW product. Another limitation is the winds, of course, are only going to be as good as your GFS short-term forecast. It is a short-term forecast, not going really far out, but if it is inaccurate, then that will obviously influence the ALPW accuracy. Here's the domain for the ALPW product. It's quite large. Extends over the North Pacific and down into South America. It's not global yet, but there are plans to make this a global product. Color tables, a word about color tables. Remember the LPW product, I talked about it, has been around for some time, and they had been using this particular color table for a while. So if you have been using this product, you may be used to this particular color table. With the new one though, this is the new default color table, and one of the notes about this is it actually takes advantage of the fact that about the highest value you'll see in this is around 1.5 inches, and anything over that you just won't see observed. So what this new color table does is take advantage of that. Anything at about 1.5 inches and greater is just saturated in this pink color. So the advantage of this color table is you get a whole lot more colors, more details in terms of the colors in here. Now feel free to experiment with the color table based on your area and also what season you're in as well. So here's our example with the old color table here, and the nice thing about this is you can see in a three-dimensional perspective the vertical distribution of the moisture over here at surface to 850, and then you can see how it lines up. This particular atmospheric river event lines up over California. Compare it to what you're used to over here in the blended TPW or the mimic TPW product, and you can see it led to a heavy rain event over here. If we're looking at a looping example of an atmospheric river, here it is coming into California, and again you can see the way that this is lined up, where the origins of the moisture, where is it coming from, and of course if you're lined up all the way through the vertical, as you know, that just increases the precipitation efficiency, and it makes for a better chance that you'll have a higher precipitation or an excessive precipitation event. Here's another example with a trough off the coast of Washington. And if you look at the TPW product, I'll just zoom in to something that you're used to here, the blended TPW. It doesn't look particularly suggestive of a really major event because the values aren't terribly high. Similar thing with the mimic TPW. But if you look over here at the three-dimensional distribution of the moisture, notice that it lines up very well in the vertical. just southeast of this big trough that you see here. So that the vertical distribution of it is quite lined up. You have very deep moisture coming into Oregon and the Washington coast. So that from that perspective, you see where the moisture is coming from, and also the three-dimensional perspective of it, how deep it is. And of course, like I said, leading to better precipitation efficiency. And here's the resulting rainfall with pretty high amounts over western Oregon and Washington in this event. We move on to our next case, and I'll stop it early on here. This is in early July, and if you're forecasting here in the desert southwest, you've been very hot and dry up to this period of time. However, you see this plume of moisture just to the south in Mexico, worried about the onset of the southwest monsoon. And if we loop this forward, you can see that moisture plume advect in to the southwest U.S. You don't see this so well in the surface to 850 because of the terrain effects here. It's a high elevation region. You see a little bit of a surge at 850 to 700, but even that's getting to higher elevation regions as you go further north. But you can see it quite clearly in the 700 to 500 and also the 500 to 300 millibar layers here. So this can be very useful in terms of monitoring the onset of the southwest monsoon. Here's another case we're going to look at. There was a flood event over Hilldale, Utah, which is right on the Utah-Arizona border. Again, surface to 850 is not terribly useful for high elevation regions, so it's not good at for this event. Over here, 850 to 700, you begin to see a moisture surge here, but where you really see it nicely is 700 to 500, and you can see that moisture plume moving towards the north. And when it moved over northern Arizona, southern Utah is when this flood event really set up. And again, you can see it was very deep. You can easily see it in the 500 to 300 millibar layer as well. For the next event, this really highlights one of the really nice applications of the Alpw product, in that you can see trajectories in terms of where the moisture has come from. For this particular event, we're going to look over northern Missouri, and in the surface to 850 millibar layer, there was abundant moisture coming from the Gulf of Mexico. Over here at 850 to 700, it was coming in something like this. And then in the lower left pane down here, 700 to 500 millibar, there was a plume of higher moisture coming from Mexico like this. And then there was a remnant tropical cyclone that had since dissipated. However, the moisture associated with it was moving across the Intermountain West towards the forecast area of interest here, towards northern Missouri. And that shows up very well in the 300 to 500 millibar layer as well. So just look at the distribution of the moisture now. If you're sitting here in northern Missouri at low levels, you're having moisture from the Gulf of Mexico. And then as you get mid to upper levels, you're getting high moisture from Mexico and also this remnant tropical system. And they're all lining up in the vertical to produce this very deep moisture that comes into play here in northern Missouri. So it gives you a great observational way of tracking trajectories of moisture. And here's the resulting rainfall amounts, very heavy rainfall amounts, a large area over 6 inches in northern Missouri. The next event, this is Hurricane Harvey, and it's pretty much going through from the development stages in the Gulf of Mexico through the devastating flood event for the Houston region. The PW values for this particular event were on the higher end of what we've observed. The surface to 850 millibar layer PW values were up to about 1.3 inches, and the 300-500 millibar layer values were up to a half an inch. Note that the missing data, in other words, these black regions, they're not lined up perfectly in the vertical. This is where precip is flagged near the tropical cyclone, for example. It doesn't line up in the vertical very well, and this is because the trajectories have different winds at different levels, typically stronger at higher levels. Since the trajectories may be different at different levels, then different satellite data may be included. So that's why it doesn't line up perfectly in the vertical, these missing data regions. The last case that we'll look at here is moving into San Francisco. And just remember to use this product for traditional synoptic and mesoscale analysis, just as you would water vapor imagery. You can easily see troughs, ridges, short waves that will be reflected in the ALPW imagery. So in this particular example, I'll go ahead and circle a short wave that was quite evident in the 700 to 500 millibar layer product right here. It doesn't really show up in the other layers. However, it showed up very well in 700 to 500, which tells you where it is. Also, this particular shortwave, when it came through the San Francisco Bay Area, there was a mini supercell event. So it did have a pretty big effect on the weather as it was moving through. And then finally, our last event here, this is the blizzard case from 13 to 15 March of last year. And you can see the system moving towards the southeast from the Midwest that helped to invigorate this surface low that you can first see in the surface state 50 millibar layer right here. And then as the circulation gets deeper, as the cyclogenesis event becomes more mature, you see it grow in the vertical. It becomes more evident at 850 to 700, and then you see it at 700 to 500, and then in the later portion of the loop down here at 500 to 300, you eventually see it. So it also gives you a good assessment of the maturity of the cyclogenesis in terms of how deep that circulation is. And you can, of course, compare that to models and see how the models are doing with it. So the other thing to note here is, of course, where the moisture plume is coming from for this particular event. And as you gain experience with this product, you'll gain a better understanding of typical magnitudes and areal coverage of moisture at different layers. So when an anomalously extreme event comes along, you'll recognize it right away. For additional applications of ALPW, see the references, additional links section on the student guide page shown here. In conclusion, ALPW provides a view of the four-dimensional structure of water vapor, including over cloudy regions. ALPW can be used for numerous applications: atmospheric rivers, flood events, convective events, short waves, tropical waves and cyclones, winter precipitation, and more. For more details, I list a couple journal articles, and the links to these are listed on the student guide webpage. How to view the ALPW product. Real-time data is available from this web page. Archive data is available from this FTP site. If you'd like to view this in AWIPS 2, CIRA distributes this to the various regional headquarters via LDM feed. If you're interested in viewing that, just send me an email. ALPW is scheduled for delivery via NOAA port SBN in 2022.